Okay. Hello everyone. Welcome to the class. This is lecture number 5. So we are in the third week of the course. What I will do today is we'll continue discussion of essentially community detection or clustering in networks, and then we will connect this back to the discussion of network motifs from 2 lectures ago. So this will kind of tie together our discussion of nodes, communities, and so on. And then for the plan for the next 2-3 weeks will be to start looking into methods for representation learning in networks. But today we are still talking about community detection in networks, and in particular what we will be interested about is how can we do community detection using spectral methods. And spectral methods meaning methods that compute eigenvectors and eigenvalues of the graph adjacency matrix. So this will be kind of very fascinating because we'll be using linear algebra to do graph processing. Okay, that's the idea. So we'll talk about spectral clustering algorithms, and spectral means that we worry about the spectra of the graph adjacency matrix, which means we worry about the eigenvectors and eigenvalues of this matrix representation of the graph. And we will go through 3 steps as we do this. First, we will do what we call pre-processing. Then we will do decomposition, where we will compute some eigenvectors and eigenvalues of some special matrices. And then based on these eigenvector representations, we will do some kind of grouping, right? So that's kind of how the lecture will go. But first, we will go and define a few concepts before we are able to go through these 3 steps, okay? So here is what is our goal. Our goal is that we are given a an undirected graph, can be weighted or unweighted. And we want to divide vertices into 2 groups that are disjoint, so non-overlapping. And the question is, how would I define a good partitioning of a graph? Right? Like last time we talked about the network modularity as a way to measure how well do we partition the graph in the groups. Right? So we will first define a different graph partitioning criteria we'll call conductance, and then we'll talk about how do we identify good partitioning that maximizes that conductance. So if modularity was more thought through from the null models and kind of physics view of the networks, this will be a computer science optimization view of the networks. So here we will actually have approximation guarantees on how well our methods work. Okay? So the goal is, given a graph, we want to find the partitions. We want to kind of cut it into multiple pieces. And essentially what we'd like to do is have a lot of edges inside the piece and a few edges across the piece, right? That we'd like to keep that type of intuition. And the question is, how do we design a formula that captures this type of intuition and that would kind of split this graph in the middle as we would kind of intuitively do? So in order to do that, we first need to define a notion of a cut. Right? And we will express this objective function that tells me how well did we find partitioning of the graph to define a notion of the cut. And we will say a cut between sets A and B, so basically we take all the nodes, we split them into 2 disjoint sets A and B, is simply the sum of all the edge weights where one endpoint is in A and the other endpoint is in B. Okay? And if you have an unweighted graph, then the edge weights are all the same and they're equal to 1. Right? So in this case, the edge cut for this particular partitioning would be equal to 2 because there are 2 edges where one endpoint is in one set and another endpoint is in the other set. Right? So essentially, intuitively, we are saying how many edges do I have to cut to get these two sets. The problem with this type of cut criteria, or one idea that we could go is to say, let's just find the partitioning that minimizes the cut. Right? The less I have to cut, the better partitions, better clusters, better communities I have found. There is a very kind of easy counterexample to this, is that if I just try to minimize the cut, then in many real networks I can have a single node kind of sticking off with a very low degree, and for this particular graph, this is the minimum cut. Right? I'm able to cut one edge, and I get set A, and everything else is set B. So kind of trivial. And I don't want to have this kind of ill-defined optimal solutions to my problem. In this graph, what I would like to do is I'd like to come up with a criterion, for example, that would cut somewhere here. in a sense that, right, there seems to be like a cluster here, there seems to be kind of a cluster here, and there is two edges crossing. So I would prefer, at least intuitively, this type of partition versus that type of partition. Yeah? Yes. Okay, great. So the problem with this, with just directly minimizing the cut, is that only kind of considers the connections between the clusters, but it does not consider what's happening inside the cluster. So a criterion that tries to fix this is called conductance. And conductance is defined the following. It says conductance between a pair of groups is their density is kind of the number, is the size of the cut relative to the density of both groups. So you say the conductance of sets A and B is the size of the cut divided by the volume, okay? And so volume is the total weighted degree of the nodes inside a given set. So volume is simply a sum of the node degrees of the nodes that are in A. So here we are saying how many edges do we cut divided by the volume we get. The reason we take the minimum is because we would like to divide this by the smallest of the two sets. And because we care for conductance to be as small as possible, we want these two sets to be as big as possible. And the minimum will be the biggest when these two sets will be approximately of equal size. Right? So here we're essentially saying I want to split my graph into two equal size pieces such that the cut is small. Right? Because if I go back to my previous guy right here and I call this set A, then I would be dividing by 1 here, and I would get a very bad conductance. I want this conductance to be as small as possible. I want to get a lot of edges inside for a very few edges that I cut. And because I take the minimum of the two sizes, I cannot make one too small. I want them to be kind of approximately balanced. So this produces more balanced or equal size partitions. And now the question is, if this is the criteria I want to optimize, how do I find a good cut? And the point is, the problem is that computing this best conductance cut is MP hard. And there is a very cute kind of proof that you can do to see this. So what we will do now is we'll talk about spectral graph partitioning that gives us an approximation guarantee to this to trying to optimize conductance or find the cut that optimizes conductance. So that's why we will talk about now about spectral graph partitioning. Right? So far I defined the criterion. Now I need to define the algorithm that optimizes that criterion. And here is now what we will do is I'll give you a quick overview of kind of linear algebra and start thinking about what eigenvectors and eigenvalues are and what is intuition behind them. Because these things are very intuitive, even though most times kind of they forget to explain it. Okay? So here is how we'll think about this. Let A be adjacency matrix of my graph. Okay, so I have an undirected graph and I have adjacency matrix. Essentially, entry ij will take a value of 1 if I and j are connected, and otherwise it will take an entry of 0. Okay? And then let x be a vector. So if my graph has n nodes, then let x be a vector of dimensionality n, and I will label its components as x1 to xn. Right? And the way I can now think of this vector x, each component of x assigns a value to a node in the graph. Right? So x1 is the value of node 1, x2 is the value of node 2, and xn is the value of node n. Right? So because x is an n-dimensional vector, there is n nodes in the network, so x assigns values or labels, you can think of it, to the nodes in G. So now I can ask myself, what does it mean if I take this matrix A and I multiply it with my vector x? Right? I can take a matrix and multiply it with a vector. You can do that, right? Matrix A is my adjacency matrix, so it's n by n, and my vector x is also n by of size n. Right? So if I do A times x, what happens? Right? Like, what is the value of y1, for example? Right? The value of y1 is that I kind of I do a dot product between the first row and my vector. And the way you can write this down is essentially you say, my value y1 or yi is a sum over the ith row of the adjacency matrix times the jth component of my vector. And if you look at what this really is, right, this will be 0 wherever if nodes I and j are not connected. So what this really is, it says yi is simply a sum over the neighbors j of node I and their values. Okay? So what does this mean? What did we learn? What we learn is that that entry yi here is simply a sum of the labels xj of neighbors j of node I. Okay? So in other words, if I take the adjacency matrix and multiply it with a vector, then essentially what I'm doing is I ask every node, take the values x of your neighbors and sum them together. And that will be stored here. Right? So a times x, the result of that is simply saying every node, sum the values of your neighbors, that's your new value y. Okay? That's very useful intuition. Okay, so that's great. Now we know what does it mean to do a times x. So now let's kind of keep working on this, right? So what we learned so far, if I take a times x, then the jth coordinate of this vector y of a times x is simply a sum of the values of neighbors of this node j. Now I can do and ask, if I think about what are eigenvectors and eigenvalues of a matrix, right? Eigenvectors and eigenvalues are solutions to this type of equation, right? A is a fixed matrix, x is the eigenvector, and y is the eigenvalue, right? So if you think about what this means that these are these special values of values assigned to nodes, such that when you sum up the values from your neighbors, you get the same value as you had, you just scale it, right? So essentially, you retain your value, it just gets multiplied. And every node in the network just multiplies their value for the same amount of lambda. And lambda is the eigenvalue, and x is the eigenvector, right? So eigenvectors are these miraculous kind of distributions or values across the nodes, such that if every node sums these values across their neighbors, their total sum just is the same as what they had before, just a bit bigger, for whatever is this lambda factor. So everyone gets their value bigger for a lambda factor, right? So what is now spectral graph theory? Spectral graph theory is a branch of applied mathematics that analyzes the spectrum of a matrix representation of the graph. So what is a spectrum? Spectrum is that a given graph, its adjacency matrix A, has a given number of eigenvectors and the corresponding eigenvalues. And the question is, what do these eigenvectors and these eigenvalues, what do they tell us? Generally, the way we will think of them is, we will think for a graph on n nodes, in general, you get n different eigenvectors and different eigenvalues, and we will think of them as ordered, so that lambda 1 is the smallest eigenvalue, and lambda n is the largest one, right? And each eigenvalue has a corresponding eigenvector. And I'll give you some examples to build some intuition, okay? So the way what you should think of right now is what is a times x, which is just you sum the values from your neighbors, and what is lambda x, where lambda is a scalar. This basically means that the value you carry versus the sum of the values from your neighbors, it's essentially the value you carry plus some constant. And this is true for every node. That's what ax is lambda x means. Okay? So let's now try to find some eigenvectors and eigenvalues of some graphs to get some intuition. Okay? So what we'll work with is d-regular graphs. What does this mean is that every node in the graph will have degree d, let's say 4. Okay? And now the question is, what are some eigenvector pairs in a d-regular graph? I'm looking for suggestions. So what's an eigenvector pair in a d-regular graph? Yes?
All ones as an eigenvector and an eigenvalue of 4.
Okay, great. So we have a suggestion which says one eigenvector is that we set all of all ones, and if I have a 4 regular graph, then lambda would be 4. Do we agree with that suggestion? And if not, why not? What do you guys think? Right, so what did we say? We said every node has degree d. So A times x is simply take the labels of your nodes. Every node has value 1 under Eric's suggestion, so you sum them up, so your value will be 4. Right? Every node does that, so every node's value is now 4. Right? So this is the eigenvector, and the corresponding eigenvalue is 4. Right? Everyone's value went from 1 to 4, so it got multiplied by 4. Right? So great suggestion, right? So if this is the vector we try, then A times x is simply d, right? Because every node just sums the values of its neighbors. Every node has a value 1. Every node sums values from d different neighbors. So the sum of d ones is a d, and that's the same for everyone, right? So, this is simply lambda times x, where lambda equals d, right? It's basically the same vector multiplied by d, right? So this is our first eigenvector eigenvalue pair. Okay? So what did we just conclude is that we found an eigenvector eigenvalue pair. Vector has all value 1s, and the corresponding eigenvalue equals d, right? And note, right, that this is just one eigenvector eigenvalue pair, and there might be others. Yes?
A dot x is the row of these.
So should I explain what A times x is?
Yeah, could you re-explain that?
Which thing I should explain?
Like why A dot x gives you, in like the then step? Yeah.
So you are a deregular graph, which means every node has degree 4. Right? If every of your 4 neighbors has value 1, and you sum up those values, what's the sum? It's 4, or it's d, right? So if everyone has value 1, and A times x says you just sum your neighbors' values, then everyone's new value will be d. We agree with that? Okay, great. So now we have the left part of this equation. How about the right part, right? Is there a relationship between these two guys? Yeah, yes, it is. They are multiplied by d. So this is lambda x, where x is this guy, and lambda equals to d, right? And we found one case. Yes?
Is there any intuition for finding other eigenpairs that have a vector that's not just ones?
Is there intuition for finding other eigenvectors that are not ones? Yes, stay tuned. Yes, exactly. That's where we are going. Okay, good point. Thank you for the question at the back. Okay, so what did I try to tell you? I tried to give you an example of one eigenvector eigenvalue pair. It turns out that D is the largest eigenvalue of A, so it means if I have a deregular graph, then this is the largest eigenvalue. All other eigenvalues will be smaller. If you wonder why, you should really... So what I will do in this lecture is I have a lot of slides that have details up there, and I won't go over them, but essentially they give you proofs for some of the claims I will make. For example, if you don't believe me that this is the largest eigenvalue, then you can find the answer here. But I won't go over these proofs in the lecture. Okay? So that's good. So you should believe me that D is the largest eigenvalue of this adjacency matrix A of a deregular graph. So now the question is, what if my graph is not connected? What if my graph is composed of two connected components? Can I come up with eigenvalue eigenvector pairs in this case? Again, this is a deregular graph, so it means every node has the same degree d. So for example, this is a disconnected two-regular graph that I have up there, right, of two connected components. So let's figure out how could I come up with some eigenvector eigenvalue pairs, right? So imagine that I put all the 1s on all the nodes in C and 0s on nodes in B, right? So here is my eigenvector, proposed eigenvector. It has 1s and it has 0s, right? And if I do A times x, as we said before, all the guys in C have links to the other nodes, so they sum these things up and they get the value d. And all the nodes in B, they have value of 0, so when the nodes in the component B sum their values together, they sum zeros together, so I get zeros, right? So I have just found an eigenvector eigenvalue pair where here's this is the eigenvector and the corresponding eigenvalue is D. And kind of symmetrically, analogously, I can define a different eigenvector. Right now, I put zeros on the component C, and I put ones on the component B. And again, by the same argument, I found another eigenvector with the same eigenvalue. Right? This eigenvector has eigenvalue D, and this eigenvector has eigenvalue D. So what we found an eigenvalue of multiplicity 2, meaning that there are two eigenvectors that correspond to that eigenvalue. Okay? So why is this important? So now we found, as you were asking, a vector that is not all a vector of ones. And what is interesting, right? If essentially one thing we kind of can learn, or at least intuitively get from this, is that if a graph has multiple connected components, then the multiplicity of the largest eigenvalue, meaning how many different eigenvectors correspond to that largest eigenvalue, will tell me how many connected components are there. Right? So for free, we get connected components. And now I tell you a bit more intuition. Right? So what we did here, when we have a disconnected graph of two connected components, and again, this is all true for D-regular graphs, then the largest eigenvalue is equal to the second largest eigenvalue, right? The first two eigenvalues are equal, right? And these are the corresponding eigenvectors, right? So now you can think that if I have a graph that's almost disconnected, has just a few kind of edges across these two components, something similar will happen, right? The largest and the second largest eigenvalue, they will be very close together, right? So what this intuition indicates is that this second largest eigenvalue will tell us a lot what nodes should be in the component B and what nodes should be in the component C. So that's the intuition, but there is still long way to get there. Okay? Yes.
All ones still an eigenvector of this?
Great point. So is a vector of all ones still an eigenvector in this space? So the property of eigenvectors is that they are orthogonal to each other. So if you dot product them, they are orthogonal. And these two guys are orthogonal. The vector of all ones is a linear combination of these two. So it's not. Right? Good point. Yes. All right. So let's keep talking a bit about this intuition, and then we'll do more math. So what we already know is that if a D-regular graph is connected, then we know that the vector of all ones is the eigenvector corresponding to the largest eigenvalue. Because eigenvectors are orthogonal, this means that the second eigenvector must be orthogonal to the first one. Right? Orthogonality means that if you take two vectors and multiply them, you do a dot product, the value is 0. So if this guy has all ones, then the second eigenvector must be such that its components sum to 0. Right? Because this times that have to be 0. So it means that components of this guy has to sum to 0. Okay? So why is that the case? Eigenvectors are orthogonal to each other. So if I write this out, basically what is a dot product? I take the xn, the first component, multiply it with the xn minus 1. So this is the second eigenvector, the same component, and I sum this up. This is all equal to 1. So, this is just 1. So this means that the sum of the components of the second eigenvector have to sum to 0. So this is a constraint that comes from orthogonality to the first eigenvector. Okay? And this fact will be important, right? So what does this mean? This means that this second eigenvector, its component must sum to 0. Which means that some of its components, some coordinates will be higher than 1, and some will be higher than 0, and some will be less than 0. And what this will mean, as I will show you later, is that some nodes will have a value greater than 0, and some nodes will have a value less than 0. And this, whether the node has a label that is positive or negative, will essentially tell us who is on the left side, who is on the right side. Okay, so the magic that will happen is that we'll be looking at this eigenvector corresponding to the second largest eigenvalue, and the sign of the value of the node will tell us is it in the left partition or in the right partition. That's the kind of preview. There is still a lot we need to explain why this goes through. Okay? Yes?
Might not be quite relevant yet, but if there's a subset of the graph E, say, and C is connected to E by one edge, and E is connected to B by one edge, and B is connected to C by one edge, this technique no longer works? How do we work this?
So if you have more than two partitions. This technique will still work if you have more than two partitions. But right now, for mathematical analysis, let's assume you have two partitions. I'll show you examples with more, right? But essentially, this is the only clustering method for which you can do math and get some sense of what is happening. The other clustering methods are more or less some kind of heuristics that you get stuck in some local minima. Okay? Okay, good. So now we kind of know what we will want to do and that we will be looking at eigenvalues and we'll be looking at the second eigenvector and we'll be looking at the components of the second eigenvector. But the thing is actually much more interesting. So the first thing is we need to decide what matrix are we going to compute these eigenvalues of. Okay? So this is just a recap. I take the graph, I create the adjacency matrix. This is the adjacency matrix. 1 means there is an edge between nodes 2 and 1, and 0 means there is no edge. Okay? Because our graph is undirected, what does this mean? This means is that our adjacency matrix is symmetric, so I can kind of flip it across the diagonal. It's symmetric across the diagonal, because if node I is connected to J, then J is also connected to I, because edges are undirected. The other important property is that it has n real eigenvalues, and that eigenvectors are also real valued, and by definition eigenvectors are orthogonal. Okay, these are three important properties of this type of a matrix. The second thing that we will do is we will define what is called the degree matrix. And the degree matrix is a diagonal matrix that has basically everything are 0 except on the diagonal, and the entry on a diagonal is the degree of that node, right? So node 3 has degree 3, node 4 has degree 3, node 6 has degree 2, right? So 6 is here, it has degree 2. That's called the degree matrix, okay? Now that we know what the adjacency matrix is and what the degree matrix is, then we define this notion of a Laplacian matrix. And a Laplacian matrix is here. Laplacian matrix of a graph, we label it as L, is a degree matrix minus the adjacency matrix. So here's the Laplacian of our graph. What do you notice? We have the degrees that are positive on the diagonal, and we have -1s wherever there's an edge. Okay? What are important properties of the Laplacian matrix? The first important property is that the trivial eigenvector of 1, 1, 1, 1, so the vector of 1, 1, 1, 1 is an eigenvector that has the corresponding eigenvalue of 0, right? Why is that the case? Because every node is summing the values of its neighbors. Because we have entries on the diagonal, we can think of this as a self-loop. So everyone is summing, the number of edges they have. That will be the minus their degree plus their degree. So this will be 0, right? So this means that x is an eigenvector with a corresponding eigenvalue of 0. And that's the smallest eigenvalue in our case, okay? So this is the first important property. We still have vector of 1, 1, 1 to be the eigenvector with a trivial eigenvalue of 0. The reason for that is that basically what we did is we added a self-loop on every node, and we added the degree. So if you sum the row, the sum equals to 0. Okay? There are two more important properties, that eigenvalues are non-negative real numbers, and that eigenvectors, again, are real, meaning they are not complex. These are the properties. Here's the proof for all these three properties. I skip that, encourage you to look at it yourself. Okay? So now I want to show one more important thing, and then we'll start working on the algorithm. For this fact is true for any symmetric matrix. And it says the following. It says that for a symmetric matrix M, the second smallest eigenvalue, lambda 2, so now the second smallest eigenvalue, lambda 2, is a solution to the following optimization problem, where I want to find vector x that is orthogonal to the first eigenvector. Here I label it as W1, and here is the equation that I'm solving, right? So W1 is the eigenvector of M with the corresponding eigenvalue lambda 1, and then the value of lambda 2 equals to this optimization problem where I'm trying to find a vector x that is orthogonal to the first eigenvector and optimizes or solves the expression above. So what I want to do now is I want to work out what is the meaning of this optimization problem for us where our matrix M is the graph Laplacian L. Okay, let's try to work this out. So here what we need to do is we need to figure out what is the value of that x transpose mx. So in our case, what is the value of x transpose L times x, right? And I'll just write it out, right? This is a sum over I and j, where for every I and j, I take xi and I multiply with xj. And here it is, right? Or another way I can do is I take the Laplacian matrix and I will expand it into its definition, right? Every entry of the Laplacian matrix is the entry of the degree matrix minus the entry of the adjacency matrix, right? I just took L and expanded it by its definition. And I'll still kind of keep massaging this, this summation. What do I do now is I take this xi, xj, and I distribute it inside, right? So I get, this is now a sum over I degree entry at ii times the xi squared, because this will happen only at places where I and j are the same. Then xi times xj is xi squared, and I have the entry, the diagonal entry of the matrix, and everywhere else, this product will be 0 because dij will be 0. So that's how I simplify this guy. And then the second guy, these aij's are just zeros and ones. So essentially what this means is rather than going over all the entries of the adjacency matrix, I can simply go over all the edges in the graph, and I multiply xi and xj. Now why do I have a number 2 here is because in this case, every edge is counted twice. There is an ij and ji. So now I only go over ij, so I need to count it twice. Okay? So now I have this. So let me keep massaging this further, right? So then what I notice is the following. If I ask, how often do I sum up this this xi squared? I sum it together d times. So the way I can write this out is I can take this and kind of rewrite it in terms of a summation over the edges, where I need to write this as x times xi squared plus xj squared. And then this part is here. So why is this summation equal to this summation? The reason for that is that here I'm basically taking xi squared and I multiply it with d. So if I go over the edges and I put xi squared here, I also get it d times, right? So, but because every edge has 2 endpoints, I have to take both endpoints, right? So that's I have xi and xj endpoint of that edge ij, right? So this part is this part, that part is that part. So what do I do? Now I think in primary school where they taught me how to work with polynomials, I can rewrite this thing as xi minus xj squared, right? You should kind of notice that. But why is this cool now? Because now I've been able to take this thing and rewrite it simply as a sum over the edges, where I take the value of node I minus the value of node j and I square it. Okay? So that's what we learned, and this is important, and we'll talk more about this guy. Okay? So I'll have this guy to show it to you. What I'm again skipping is this fact why second eigenvalue is the solution to this particular minimization problem, and why the second eigenvector is the solution of this minimization problem. Okay? So that's the proof here. Please check it yourself. Okay, this is the reason why. Okay, so now the question is, let's try to find x that solves this optimization problem. Okay, so the idea is the following. What do I know about x? I know x is a unit vector, right? Because it's an eigenvector, eigenvectors have unit length, so the sum of the entries of xi squared equals to 1. Its Euclidean length equals to 1. The second thing I know about x is because I'm doing this over the Laplacian matrix, I know that the first eigenvector is all ones. And I know that x is a second eigenvector, so it has to be orthogonal to the first one. So we talked before, right? So if the first eigenvector has all value ones, and I dot product x with it, I have to get a 0, which means that the sum of the entries of vector x has to be 0. So these are two important facts. First is x has Euclidean length 1. Second important fact is its components sum to 0. This is just from the fact that the vector of all ones is the eigenvector of the graph Laplacian, and eigenvectors are orthogonal to each other. So now I will go and restate that equation in the top right corner, what we did in the previous slide, right? So I can restate the equation up there over the graph Laplacian as the following, right? Saying lambda 2 is a solution to the following optimization problem. Find a vector x such that its components sum to 0, such that its Euclidean length equals to 1, and in such a way that when I go over the edges of the graph, the value of node I minus the value at node j squared, the sum over these things is as small as possible. And the value of the sum equals the value of the second smallest eigenvalue. And the vector that gives me these solutions, this vector is the eigenvector corresponding to the second smallest eigenvalue. Okay? So what I want to do now is look a bit about this, right? So remember that the entries of vector x sum to 0. So some of the entries have to be positive, some of the entries have to be negative. So the way you can think of this is the following, right? I want to minimize this sum. So this means, and as I said, some of the nodes of my graph will be kind of will have their label assigned by x to be less than 0, and some others will have the label assigned to be more than 0. All right? If nodes are connected that are on the same side, then here in the difference, this will cancel out, and the square of that will be small. Right? And this, in some sense, error or distance will be big when I take a node on the left side of 0 and I take the node on the right side of 0. Right? So this essentially, you can think of this is the distance between the node labels in this case. Right? So, and I will only take nodes I will only cross 0 when I have an edge that crosses 0. Right? This is when this value will be big and the square of it will be even bigger. Right? So essentially what I'm trying to say is that in order for us to minimize this, what we want to do is we want to take nodes that are connected on the same value here so that these differences will be small. But we have to do it such that we put about half of the nodes here and the other half of the nodes here, because the sum over the coordinates has to be 0. Right? And then the only time when this error or this term will be big, when an edge goes across 0. Right? So by solving this minimization problem, we are essentially putting about half of the nodes to the left of 0, half of the nodes to the right of 0, such that the number of edges that crosses is as small as possible. Okay? Do people see that? Yes, awesome. How about this side? Sleepy, but yeah. Do you guys agree with what I say? Yeah? So what you should see, and let me know if you don't, is that this optimization sum, what this is doing is essentially saying, I will assign a value to every node. I have to assign values to the nodes such that the sum of all values is 0. And I'm doing this, I'm computing these differences across all the edges. So this thing will be large when I have an edge that between nodes that are on the that have labels on the different side of 0. This will be large. If the nodes are on the same side of 0, this difference will be small. So our goal is to, in some sense, assign values to nodes such that the fewest number of edges crosses the 0 line. That's what this optimization problem is doing. Okay? So that's great. So now we kind of know that this is something very magical. And here is the explanation why this lambda 2 is the magical eigenvalue. And that the eigenvector that corresponds to the lambda 2 is the magical eigenvector, because it kind of puts nodes to the left and to the right of 0. And here is the reason why it does that. Okay? So now let's go back before we were all born, when there was this guy from Czech Republic, Fiddler, who came up with the following idea. He said, let's express the partition of the graph into two sets A and B with a simple binary vector, well, where we'll have the +1 value if at coordinate I if I belongs to A, and -1 if if that node belongs to B, right? And if I enforce that A and B are of the same size, then the sum of the components should equal to 0, right? There will be a same number of +1s and -1s in this vector, so sum of the components will be equal to 0, right? Which is equivalent to saying that this means that this vector y is orthogonal to the trivial eigenvector of 1, 1, 1, 1. Then he said we can minimize the cut of the graph partitioning by finding the vector y that minimizes the following expression, right? He's like, let's find the vector y where every coordinate of the vector can only take a +1 or -1, such that when I take these labels, sum them over the edges, the sum of the squared differences is as small as possible. Notice that this is exactly the problem we were trying to solve. The only difference was that here Fiddler said this can only take value +1, -1, and our vectors have general real values. But what this is essentially saying, it's saying put half of the nodes at coordinate -1, put the other half of the nodes at coordinate +1. So all the edges that are between these nodes will cancel out. We'll have 0 here. All the edges between the nodes that are here, again, will cancel out and will be 0. And the only time you will pay a penalty is whenever the edge crosses, right? And this will be, so you will get a penalty of 4 for every edge that crosses. So the value of this expression will exactly count the number of edges that cross the two partitions. That here I assumed or enforced that they are of equal size. Yes?
How are we enforcing that the partition is balanced here?
Sorry?
How we are enforcing that the partitions are balanced?
How are we enforcing? I should write as a condition here.
Were we enforcing that in our previous example? You mentioned half on either side, but I don't remember if we were enforcing that or not.
In the previous example, we were not enforcing it. All right? But again, what you should notice from here is this similar type of optimization problem. Okay? So now here is what is, so there is a Fiddler, and people will call it a Fiddler vector, and it's a very kind of classical term in spectral graph theory. Then another classical result from the spectral graph theory, it's called the Rayleigh Theorem. And what this Rayleigh Theorem says is that if you compute the expression we talked about before, then you enforce that the values of this vector y sum to 0, and that the vector y has Euclidean length 1, then that the solution to this optimization problem is lambda is the value of the second smallest eigenvalue. So this means that the minimum value of this f of y is given by the second smallest eigenvalue of the graph Laplacian matrix L. So this says that the solution to the following optimization problem, where now we allowed y to take real values, but its components have to sum to 1, and the squares of its components have to components sum to 0 and the squares sum to 1, then lambda 2 is the solution to this optimization problem. And then, or is the value of the optimization problem. And then the x, the eigenvector corresponding to the second smallest eigenvector, is the other part of the solution to this problem. And this eigenvector x that corresponds to the second smallest eigenvalue is called the Fiddler vector. So if somebody says Fiddler vector, this is what they mean. And what is the consequence from all this is that we can use the sign of this Fiddler vector x to determine whether a node is on the left or on the right side of the or in the left partition or in the right partition, right? So the picture to think about is something like that, right? Where y are these coordinates, and then the differences squared essentially count how many edges cross. And why is this important? This is important because there is a beautiful theorem, again, proof follows, where you can show that this type of spectral clustering of this graph Laplacian will give you a near optimal solution. So essentially what this is saying, if in the graph there exists a cut of conductance, now remember we defined conductance at the beginning of the lecture of conductance beta, then lambda 2 will be smaller than 2 times beta. Notice that smaller is better. So this means that I have found something that is a factor 2 away from the optimal solution, right? Because lower is better. So essentially it means that if the second eigenvalue will give me a cut of conductance that is at most 2 times worse than what the optimal cut would be, which is NP hard to compute. And when I say optimal cut, I really mean cut of the optimal conductance, not the cut metric itself. Okay? So this is what I wanted to tell you. I'll skip this. This is what I wanted to tell you about kind of mathematics of this, right? So what did we do? We defined the score for the goodness of the graph, which is called conductance. Then we said, how do we efficiently identify the partitioning that achieves good conductance? We said, let's approximate the information provided by the eigenvalues and the eigenvectors of the graph Laplacian matrix, and then this whole thing is called spectral clustering. Okay? So now with kind of this mathematical intuition, now I actually want to show you how these things are really done in practice. We can take a bit of a break, and I'm happy to take a couple of questions, if there are any. Yes, go ahead.
So, put another way, is solving for lambda 2 like solving these squares between these two?
Exactly. Putting the other way, all I said, right, is that solving for lambda 2 is essentially minimizing the sum of the squared differences between the coordinates of nodes, right? With the condition that the sum of the node labels should be equal to 0, which means some are on the less than 0, some are more than 0, and the sum of the squares has to be equal to 1. Exactly. That's exactly what we did. All right? That's a beautiful summary. Good. So let's now move on and go back to my first slide, which was how do you do spectral clustering? You do pre-processing, you do decomposition, and you do grouping. We already know what the pre-processing we do will be. We will create the graph Laplacian matrix, right? So if I take the graph, I will define the degree matrix, and I will then create the graph Laplacian matrix. Then I will do the eigen decomposition of the graph Laplacian matrix, and all I care about is the second smallest eigenvalue and the corresponding eigenvector. Everything else I don't care about, right? Notice that the smallest eigenvalue has value 0. Here is the corresponding eigenvector. All the components are the same. They are not equal to 1 because all the eigenvectors have length of 1. This is the second smallest eigenvector, or the eigenvector corresponding to the second smallest eigenvalue. Here I'm writing the coordinates of it again. Notice that the first 3 nodes have a positive coordinate and the last 3 nodes have a negative coordinate. Okay? So this is the first part, right? I create the graph Laplacian and then I do the eigenvalue decomposition. And the way you can think of this is now that this maps the nodes of the graph into coordinates, right? Every node has a coordinate assigned. And the point is that the sum of these coordinates is 0, and the sum of squares will be 1. This is by the kind of the constraints coming from eigenvalue decomposition. Yes?
Is there an intuitive way to think about how eigenvectors relate to an adjacency matrix?
Is there an intuitive way?
Besides just there's some like individual eigenvectors.
An intuitive way how eigenvectors correspond to the adjacency matrix. I mean, we talked about the spectrum allows us to uncover the connectivity, how many connected components we have. The second eigenvalue allows us to partition and reveals the conductance. And then the higher order kind of eigenvalue provide kind of higher order kind of moments variations across of this adjacency matrix. What people really care about most often is lambda 2. You can look at other ones as well, and there is some theory about that. But the theory is the most well developed for lambda 2. Okay? So now we told about how to compute that eigenvector. So now we need to do the grouping, which basically means that we sort the components of the second eigenvector based on their value. And then we simply decide to split on 0, right? A naive approach would be to split at 0. People use more expensive approaches to maybe to minimize the cut in one dimension, or somehow empirically decide the threshold, what to put on the left, what to put on the right. But if we would just do what I told you so far, all the nodes that have the positive value in the eigenvector go on the left, and everything else goes on the right. So in my case, I would put 1, 2, and 3 in one cluster, and 4, 5, and 6 in the other cluster, right? So that's cluster 1, that's cluster 2. Here was our original graph, so we exactly recovered the cut we wanted to recover. Okay? So it's kind of magical, right? That I create some matrix, I compute some eigenvectors and eigenvalues, I look at the components of the second eigenvector, and this essentially does the clustering for me for free. That's kind of the magic here. And I can even show you, for example, if I take a real graph, here it is, and I create the graph Laplacian out of it, and I compute the second eigenvector, and I simply plot the values of the second eigenvector from the smallest value to the largest. Notice how it nicely splits the nodes, right? Like about half of the nodes has the negative value, about half of the nodes have a positive value. So it's very easy to say, this is my cut, and it will correspond to this. Notice also that on every side I have kind of two nodes that are a bit closer to 0 than other nodes. These two nodes are these guys and these two guys, right? So notice again how beautifully captures the structure of the graph. And then somebody was asking me, what if I have 4 clusters? Here is an example of a graph, and its corresponding second eigenvector, right? So here I have kind of 4 clusters, and notice how I get these 4 stairs. Yes?
What if you have more than one connected component? Is it like the second eigenvector or eigenvalue is corresponding to the largest ones?
So if I have multiple connected components, then of course my theory will break, right? Then the second eigenvalue will be the same as the first one, right? So that's a kind of a trivial case. Here I'm assuming the graph is connected, right? But if you have a disconnected graph, you won't apply the eigenvalue decomposition to figure out that it's disconnected.
But can you do the same thing to find the clustering within the connected components?
Oh yes, of course. You can just take the connected component and run your method on it, right? So that's very doable. So I'm not sure why are you kind of asking me this? It seems like not important. I don't know how to say. Like, sorry, right? Like, if the graph is disconnected, then yes, of course, we showed the result before that then the first and the second eigenvalue will be the same, right? We showed that. But this means we found perfect clustering. We found the clustering of our disconnected graph into two communities where we don't have to cut any edges. Like, that's the best thing that can happen in life, right? So, but if the things are a bit more complicated, then it nicely explains them, right? So I think what you just asked, maybe I will change my answer. We can still do what you said. In that case, it's the best thing. We get the best possible cut. We get the cut where we don't have to cut anything, which is the best cut to do in, like if a cake comes pre-cut, there's nothing for you to cut, right? Which is the best scenario. So it's like getting a cake. It's a free cake, all right? So it's not a bug, it's a feature. That's the point, okay? But of course, if the cake is not entirely cut, like here, you have to cut it and the second eigenvector will still tell you how to cut it. Okay, good. Thank you for the question. Good, yes?
You have to tell it how many times to cut it, so like the number of clusters you want.
Great question, right? So far I only did it for 2 clusters. Here I show you what happens if you kind of have 4, right? So what do people do? One option is to look at this and try to come up with some heuristic that will decide to cut it. This is what people do. The other thing people do is they, let me show you a few more examples. I'll come to that question. Is there anything else? Yes?
Can you also use the information from the eigenvectors corresponding to the third or fourth, even more?
Great question. So the question was, can you use information from third and fourth eigenvector? This is the answer to his question. So I'll come to that. Yes?
What if your clusters aren't like split in half? What if you have a small cluster and a large cluster?
Great. What do you do if you have a small cluster and a big cluster? The conductance metric kind of takes account for that, right? It has some preference for kind of balanced partitions, but if it's a small cluster that's super well defined or barely connected, it will prefer that over something that is worse. So it kind of accounts for that, right? This is what I wanted to show with something that has 4 clusters and the corresponding second eigenvector. Here is this was the question. This is now x3. I showed you, this is the graph we had before. This is x2, so the eigenvector corresponding to the second smallest eigenvalue. On the top, I show you x1, and you see all the values are the same, so this is our trivial eigenvector, right? Why it doesn't have values of 1 is because the sum of squares has to be 1, so it's just normalized. But this is now x3, right? And notice how x3 has interesting structure. It's negative, and then it's positive, and it's negative, and it's positive. And this corresponds exactly to negative, positive, negative, positive, right? So this now says that you can use this information together with that one to identify the partitions. So going back to the questions you guys asked, what do people do to identify partitions? One is that they do this recursive bipartitioning. They find x2 cut in half, right? So the idea would be that here, first is cut this in half, and then take each of these 2 pieces, and essentially then this thing will be magnified by x2, and that thing will be magnified by x2. So you can kind of recursively apply it and cut it in half and keep going down. That's one strategy. The other strategy is that you cluster based on multiple eigenvectors, right? That you take x2, you take x3, you take x4. So now every node is described by multiple values, and you essentially run k-means on this embedding of nodes in this k-dimensional space, where k is the number of eigenvectors you take. You skip the first one because all the nodes have the same value, but then you take 2, 3, 4, and so on, right? And people do that, and it works well in practice, and it's it's used, and it's kind of a newer method. And this is what people prefer rather than doing this kind of hierarchical partitioning, but essentially all the math has been done for this case, right? Because splitting in 2 is as hard in splitting in more. Okay? Yes, sorry, go ahead.
K clusters use k minus 1 eigenvectors, excluding the first one.
No, that's not necessarily. So the question is, what do you set the value of k to be? K is not the number of clusters. K, you pick a couple, right? So here, for example, just x2 and x3 already distinguish 4 clusters. So the thing is, you take the first couple, I don't know, 5, 10 maybe, even if you want to identify hundreds of clusters. You don't need to go so deep to now need to compute the first 100 eigenvectors, eigenvalues, because they get very unstable later on numerically. So you compute the first few. Yes?
But choosing that number is probably difficult in practice.
Great, but the question is, how do you choose the number of clusters? There are ways to do that. There is many different ways. I will show you one way how to do that.
Actually, meant the number of eigenvectors.
I will also show you how to choose the number of eigenvectors. Give me 2 slides. All right? Good. Anything else? All right. So why do you want to use multiple eigenvectors, right? Why go after this Shi and Malik proposed solution? That was actually come from computer vision to do object segmentation, and they represented it as a graph and did these things, right? So it approximates the optimal cut in terms of this k-way normalized cut or a k-way conductance-based cut. It emphasizes this notion of cohesive clusters, the way we talked about conductance, where we are trying to maximize the conductance. Multiple eigenvectors are also nice because they prevent kind of instabilities due to sure, information loss, but really due to numerical instabilities and your non-perfect precision when you are doing things numerically. So people like working with multiple eigenvectors. Now, how do you decide how many to take? One rule of thumb is that most stable clustering is generally given by the value of k that maximizes the eigengap. And the eigengap is the distance between the k and the k minus first eigenvalue. And usually you can plot them the following way and then decide where you want to cut. Right, so the way these things will look like, if you have a lot of clusters, then the eigenvalues will be high and then they will drop. And whenever they drop, this is how many you want to take. Right, which goes back to this intuition that I was telling you before. If our graph is disconnected, then the first two eigenvalues will have the same value. So if our graph would be disconnected, lambda 1, lambda 2 would be the same, and then it would drop off. So if our graph is almost disconnected, then lambda 2 and lambda 1 will have about the same value. All right? So now, depending on that, I want to take as many until this kind of drop happens. So in our case, I would choose k equals to 2, so I would take the second eigenvalue, and I wouldn't go further down. Okay? Good. Yes?
When we had the constant d graph, the maximum eigenvalue was d. Is there a maximum of the diameter of the graph?
Great. So the question is, what's the maximum eigenvalue? What we did, and I kind of didn't explain that. What we did is, because for a general graph, the maximum eigenvalue will correspond to the density of the graph and things like that. What we did is we created the graph Laplacian that kind of flipped the spectrum around, right? So the largest eigenvalue d mapped to the trivial eigenvalue of 0. So that happened somewhere in there that I did not explain too well. But right, what happened is, rather than worrying about the biggest guy, we transformed the adjacency matrix to take the biggest guy and mapped it to the eigenvalue of 0 for the same eigenvector. Right? Before we had the eigenvector of 1s had the eigenvalue d. Now the eigenvector of 1s in the Laplacian has the eigenvalue 0. And all we care about is that second smallest guy. So I don't need to say what happens on the other end. Right? We don't know. All right, good. So let me now tell you about a super exciting extension of the spectral clustering method that we actually, that one of my PhD students developed, I think 2 years ago, and he's now teaching at Cornell. But here is the idea. The idea is, we talked about this spectral cluster, like about network motifs as these building blocks. And here are the 13, directed motifs that you can look at. And the question is, could you come up and cluster the network based on the motifs? Right? So what I want to do is I want to detect communities based on network motifs. So let me explain what the idea is. The idea is, if you take the network and you take a motif, then I would like to somehow identify clusters in the network where this motif occurs a lot. Right? So for example, if this is the motif of interest and that's the input network, then here I try to illustrate the instances of that motif, right? It's like 2 edges out and a bidirectional edge. 2 edges out, bidirectional edge. So the cluster I would like to identify would be this cluster, okay? Because I have instances of my motif. But for example, if I, right, so show it again. For this motif, this would be the clusters for a different motif. Now I have 2 bidirectional edges and a unidirectional edge. The clusters I would want to identify would be these clusters, right? Because I have bidirectional edges and a unidirectional edge, right? So the point is that different motifs will reveal different clustering structure. So the question is, can I cluster my network based on the motifs? And what is super cool is that this 40-year-old mass theory that I was telling you about generalizes to this type of a case, right? So what's the idea? The idea is that what we did so far, we defined what is the notion of number of edges cut, we defined the notion of the volume, and then we set conductance is number of edges cut divided by volume. Okay? So now let's see what if we want to extend these definitions to the notions of motifs, right? If I care about finding the cluster of motifs, then the question is, do I cut the motif or not? So cut of the motif will simply be the number of motifs endpoints that get cut, right? So this is cutting the motif. And then the definition of the, this is of the cut. Definition of the volume is just how many instances of motif or how many endpoints of the motif are there in a given set. And then the conductance, this motif-based conductance is number of motifs cut divided by the volume, right? So in some sense, we just in a straightforward way generalized our definitions of cut, volume, and conductance to the notion of motif cut, motif conductance, and motif cut, motif volume, and motif conductance. Okay? So let me give you an example. Imagine this is the motif of interest, and here is my network. Then, for example, we want to ask what is the conductance of this cut, right? And we care really conductance with respect to this motif. So the way I would think of this is to say, let me identify the number of motifs cut divided by the motif volume. So if I look into this graph, here are all the instances of my motif, right? It's a bidirectional edge and two edges pointing out. So these are all, these are 3 plus 3, 6 instances of my motif. So how many motifs does this cut? It cuts one instance of the motif, right? These edges do not participate in the motif, so I don't care about them, right? So we know that this will be equal to 2. And now what's the volume? The volume will be how many instances of the motif are on the side S, right? So it's 3 instances of the motif. Each instance has 3 nodes, so it will be 9 plus this node counted from this motif, right? So the motif volume will be 10, and the number of motifs cut equals to 1 here. So the conductance is 1 over 10. Okay? People followed? Yes? Yes?
Doing the min anymore?
Why are we not doing the min? Right now I'm just illustrating you the notion of how do you compute the conductance, motif conductance of a given cut. And then the question will be, how do I find a good cut?
Of the volume, of the 2 volumes on opposite sides of the cut.
Great. Why am I? I'm just lazy. We are still doing the minimum of those things, but it's kind of cumbersome. Yes. So, lazy.
Can you again define the motif volume? Like how did it come out to be 10?
Why is it 10? Yeah. This is the number of motif endpoints in the set S. Motif endpoints, right? So a triangle has 3 endpoints. So there are 3 triangles here. So that's 3 times 3. Plus this motif has 1 endpoint in S. So it's 9 plus 1. Good point. Thank you for asking. Okay. So now what I want to, now I showed you if somebody gives me the cut, how do I compute the quality? Now the question is, how do I find automatically good cuts? How do I find clusters of motifs? And the bad news is that, again, if just finding an edge cut is NP-hard, this is also NP-hard. But there is also good news. The good news is that we can generalize spectral clustering that I told you in the first part of the lecture to this more complex type of cutting. And the idea is that on the input I get the graph and the motif. I will take the graph and form a new weighted graph. I will call it W, and it will have a superscript M, because W will depend on M, the motif of interest. I will apply spectral clustering to this W, and I will output the clusters. And there is a theorem that basically says that we get the same guarantee as for spectral clustering on edges, that the resulting clusters will be near optimal with respect to the motif conductance, right? So we get the guarantee. So what are the 3 steps? The 3 steps are the same as for ordinary spectral clustering. We will create this graph W. the way we will create the graph W is the following. If I have a graph G and a motif of interest, then I will create an undirected graph where the weight of every edge will be the number of motifs that this edge participates in, right? So for example, this edge here between 6 and 7 has a value 1 because it participates in one instance of the motif. Edge 8, 9 participates in two instances of the motifs, so it has the value 2. Edge 9, 7 participates in 0 instances of the motif, so it has weight 0, so it doesn't exist. Okay? So this is now my WM. Okay? And I will apply spectral clustering to this WM, and then based on the second eigenvector of this WM, I will determine the clusters. So let me now show you how this will work, right? So I have my motif of interest, I have my input graph, and as I said, I will define this weighted graph W, where the weight of every edge will be number of times this edge participates in my motif M, right? And I already explained you why this edge has value 2, why some other edge has value 1, and so on, right? So this is the pre-processing. Now that we have done this pre-processing, the main insight is the following. If we apply normal spectral clustering to this undirected weighted graph W, then the clusters it will produce will have optimal motif conductance. So essentially, by clustering this graph, we get clusters that optimize motif conductance. Even though the clustering method will optimize edge cut on this, so the conductance, like the normal edge conductance on this thing, the clusters will get out will be optimal with respect to this metric as well. Okay? So what does this mean? This means the following. In the first step, given the graph, I form this weighted matrix W. Now, given this weighted matrix W, I can think of as a weighted graph. I basically go create the graph Laplacian. Right, here's my W, the degree matrix. I create the graph Laplacian and find the vector x that corresponds to the second smallest eigenvalue of this graph Laplacian. And now this x will reveal communities to me. Here is one way to think of this. The way you can plot things now is to say, let me sort the nodes in X according to the value in the eigenvector, right? So these are x1, x2, x3, x4, x5, and so on. And these nodes are sorted so that this is the smallest value of x1, the smallest value in the vector x, and this is the largest value in the vector s. And then what this is trying to show is, what is the motif conductance if I only take the first node and say, this is the cut, this is the rest of the network, and this is the left-hand side of the network. Or if I take the first two, or if I take the first three, the first 4, 5, and so on. What you notice if I plot this which is called sweep procedure, the value of conductance is minimized here. And if I look at what are the first nodes with that have the smallest, the 5 smallest values in the second eigenvector x, this is the subgraph of the 5 nodes that have the smallest value. If I go back, right, this was the graph, and the first 5 nodes are these nodes up here. So essentially, the point is that we are able to identify these clusters, right? So what are we doing here? Rather than splitting on 0, we are doing this sweep procedure, where we sort the nodes based on their values in in X, and then we are repeatedly taking the first R elements of X and ask what is conductance. If we take the largest element, the 2 largest, the 3 largest, 4 largest, 5 largest, and we create this thing, and wherever it reaches the global minima, that's the best partitioning of the 2 clusters according to the second eigenvector x. Okay, so this is what I tried to explain, and this is a bit different than what we were doing before. Yes, go ahead.
So this
function of this conductance looks like it's convex. Is it always the case?
So it looks like it's convex. Usually it's not convex. So you need some heuristic to decide what to take, where to stop. So usually it's not convex. It just says if you sort the nodes by the value in the second eigenvector and you take the first R nodes, what's the conductance of the first R versus the rest? Yes?
You mentioned that this produces an optimal motif clustering. Do we have any guarantee on the global optima? Like
Great. So do we have a guarantee? We essentially have a very similar guarantee than what we had for spectral clustering. The only difference is that we had number 2 here before. Now we have a 4, and we had just the value here. Now we have a square root. So essentially, we pay a quadratic price, right? Before we had factor 2. Now we have a quadratic approximation. So there is some price, but theory still goes through. Okay, and the details are in the paper. Okay, so let me summarize. So how do we do this more advanced way of clustering? Essentially, we take the graph, we pre-process it to create this undirected weighted graph. We apply spectral clustering on this, and this will give us near optimal higher order or motif-based clusters. So I want to show you, I have 3 minutes, I want to show you one example how this works. So what we will be looking at is what are called food webs. Food webs are networks where nodes are species animals, and edges are carbon exchange. And carbon exchange is fancy word to say who's eating whom or who's preying on whom, right? If I would give you my carbon, that would mean you'd eat my flesh, essentially, right? But that's the point, right? It's about who's preying on whom. How is essentially the energy transferred in the ecosystem? That's what these networks try to capture. And essentially, they have these prey type relationships, right? And the question is, can this tell us how these ecosystems are organized? And in particular, we will be looking at the ecosystem from the Florida Bay, which is a marine ecosystem. You have kind of animals at all depths, and you know which animal is a food source for what other animal, right? So for example, what is the picture? What would be what is the explanation of this motif? This would mean that this particular animal is a food source for the other 2 animals, where the top one is also a source for the bottom one. For example, this would mean that the bottom 2 animals have the common food source and they prey on each other. Or here is 2 animals have a common food source, so they both prey on this one, but they don't prey on each other. So there is a biological explanation for each one of them. So what we can do is we can say, can I take my network, try to partition it based on each of the motifs and see using what motif do I get good clusters. So the way you can do this is the following. This is now different motifs. For every motif, I get this curve as I showed you before, right? And notice that these curves are non-convex, as there was a question before. But what do you notice, right? This is conductance, so lower is better. You see, for example, that for motifs M8 and M5, this curve very slowly goes down and it doesn't really reach anything low. You see that for this motif M6, it reaches minimum very quickly. It very quickly decays to a good value. So this means that M6 has some biological significance and kind of reveals the clustering structure of this network, right? So the first thing we learn is that the network is organized based on this motif M6, but it's not organized on M5 or M8 because we don't see any good cuts in this profile plot that I showed you before. So that's the first important thing we notice. The second important thing we notice is that this is a very interesting motif. And what this is saying is that basically the way this network seems to be organized is that you have this type of structure where you have animals who have a common food source, but then they also prey on each other. And this kind of indicates this type of layer structure where you can think that you have animals here who prey on each other and they all prey on the things above them, right? And if you look into this, if you actually plot the network and look what is happening and what are the clusters you identify, you exactly identify the clusters that correspond to what biologists say aquatic layers, right? Where you have some little fishes, you have micronutrients, you have some microvertebrates, and so on, right? So the idea is that basically what we are able to find is we are able to find this kind of layers in the ecosystem. And if you look at these clusters, here they are not so clear, but if I look at them individually, here is how they look like. And notice how these are just instances of this motif, right? So for example, needlefish and some other fishes are preying on each other, and they have all these other common food sources. Here they are, right? Both of them prey on them. Or here's another cluster where the way this works is that you have bidirectional edges are now here between free bacteria and all these other plankton type species, and free bacteria either feeds on the input to the ecosystem or feeds on the carbon that is in the water, right? Again, notice that these are just instances of this particular motif where bidirectional edges are here. So really, the clusters have this type of structure, and we were able to discover both the motif as well as the structure of these clusters, and notice how essentially these clusters are composed of many instances of this motif. So I had one more example. I won't cover this. I will finish here. Thank you very much. If anyone has any questions, please come talk to me. Thank you.